We'll continue with the with the promise I made, I guess. So we mentioned, we mentioned yesterday what I wanted to do, which was to get to show that that the ground state of the toric code is not plugged. Oh yeah. Right. Yeah. Let me ask. Okay. Yeah. Thank you. Yeah. So what I promised that I would do today is to show that the ground state of the toric code, which is this Hamiltonian here, can be written down as a convolutional neural network with the structure that I motivated yesterday, right? Like with these filters that we discussed, and with this architecture, and that the only thing that we had to do was to remove one of these neurons, okay? And so that would correspond, if we made a coherent superposition of the amplitudes given by this neural network, then that you get this ground state, okay? So, and today I'm gonna briefly describe this, this Hamiltonian, the toric code, and its ground state in a very basic way. To make connection with this game or this toy model that we came up with yesterday. Okay, so let me briefly go back to the Blackboard and describe the toric code pretty quickly. Okay, so let me do it here. So this toric code. So it's that Hamiltonian that you see there, right? Like it's a sum of terms, the plaquettes, a plaquette operator minus sum over the vertices of this operators, where this BP are products over the plaquettes on the lattice, right? Of sigma, so I in the plaquette. X, and the A, V are these operators. So again, products over J in the vertex V of sigma J X, okay? And the lattice, as I said, looks like this. As we said yesterday, so it looks like this. So we have the usual square lattice, and the spins live on the edges of the lattice, so they live on the edges. So and so what I call a plaquette is this group of spins, and so So yeah, those. So when I say there's a product over the spins or the spin operators on the plaquette, we mean this 4. And when we say there's a vertex, what I mean is this, and so V, and the 4 spins that I mean, or the 4 operators are those here. Okay, so so a couple of observations. So this Hamiltonian has a very special structure in that all VBPs and AV commute. Okay. Okay, so that's important. That's because, so we can write this down in this way: AI, AJ equals B, BI, BJ equals AI, BJ equals 0. Okay, and why is this so? It's because every time you, so when they do not overlap, they obviously commute. But when they do overlap, say this and this vertex, there's only a pair, there's always a pair or an even number of Pauli operators that are both in the A and in the B. Okay, and if you write this down, like for instance, you could let me see if I can do it quickly. Let's call this A, B, C, and D, and this E and F. Suppose we're talking about this vertex here and this plaquette here. Then the vertex is, okay, X, 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 and A, B, C, and D. And so if we're computing the commutator, we compute the products between, say, A and B. And so you have here B, so Z. And you have here D, C, E, and F. Okay, and so there's 2 common sites, which are these are, in this case, D and C. So this one's here, and those here. And the key is that sigma X, I, and sigma, they anti-commute. Okay, this is a property of the Pauli matrices. You've seen some of this in the morning, right? And so when you switch this one with this one, you get a minus sign, okay? And when you switch this one with this one, you get another minus sign. And then, because of that, the commutator becomes 0, okay? So so that's how you prove all this, these commutators, or the fact that this operators commute, and so that's makes things easy. So H is at this point, H is a sum of commuting terms. Commuting terms, which makes our life easier because then we can construct the ground state analytically as simultaneous eigenstates of all the individual terms, okay? So ground state is a eigenstate of all terms in H. Okay, is that okay? Okay. So let's look first at the B terms. Okay. So if you remember, B was the thing that we considered yesterday, right? Like the quote unquote classical part of the Hamiltonian, which was this part, right? The Ising gauge, the Wagner's Ising gauge theory part. So let me first focus on thinking about the wave function in terms of the basis of eigenstates of the sigma z operator. Okay, so how does this look, right? So okay, so let's see how so. Right, so, and then, okay, before I do that, then let's take a look at this piece, right, which is what we're doing. So how would you minimize the energy of this Hamiltonian, of this part of the Hamiltonian? Anyone want to guess? If the products over the spins on the plaquettes in the computational basis are 1. So that's what we mentioned yesterday, right? And so if we think about the ground states or the configurations that contribute to the ground state in this basis, and they're due to the presence of this term, so then you'll get that the products or the plaquettes are 1, right? So, which is the same as the ground states of the Ising gauge theory that we discussed yesterday. All right. All right. So let me draw a figure again about those configurations. Okay, and I'm going to draw a particular one. So a specific configuration. Okay, this is too large, but let me do it just. So I'm going to try and draw a configuration that looks like this. Okay, that is a ground state of that Hamiltonian, or that term of the Hamiltonian in the computational basis. So let's say we're looking at the sigma z basis for writing the wave function. Okay. Okay, this is going to take a long time, but I should have drawn a picture on a slide. Well, you get the point. So, and I'm going to call open circle up, okay? Or sigma z is 1. And dark, or let's say yellow, that's down or -1, okay? All right, so I'm going to draw. So whenever there's nothing, let's assume there's a white empty circle, okay? So as it is, it's all spins up. This is a ground state of this part of the Hamiltonian, right? Or an eigenstate, or with low energy of this object here, because the products over all the plaquettes are 1, okay? But let me draw one where when you have some spins down as well. Okay, and then I'll play with this. Okay, so this one, can you tell me if this one is a low energy state of this part of an eigenstate of this part of the Hamiltonian with low energy? So why not? But if you take a look at the plaquettes, so this plaquette is it satisfied or not? So this one is satisfied, this one is satisfied, this one is, this one is, this one is, this one, this one is, this one, all of them are satisfied. Which one? Yeah, but these are, we're looking at this computational basis, right? So they wouldn't have to be satisfied if we were looking at it in this X basis, right? So they don't have to be satisfied, all right? But the vertices are. And I guess the important thing that I want to emphasize or that we want to notice is that that if we look at how this that what I want to see is that if we connect these spins on the across lines on the dual lattice of the square lattice, this is what you will see. Okay, let me. Okay, so I'm gonna draw this line here. So this is. Okay, so what you see is that this configurations where you have spin down, they form a loop, okay, in the dual lattice of the system, and you can start flipping more and more of those. For instance, you could flip, let's say, this one here, this one, this one, this one, and this one. So this one, so again, is a ground state or is a low energy eigenstate of that whole operator because all the plaquettes are happy. And if you draw, what? So if you draw the same thing again, these again form what? Form a loop, okay? And so in this basis, in the set basis, what you see is that configurations that should contribute to the ground state of the quantum state of the toric code form loops, okay, in a background of, say, spins up, okay? You can keep adding defects and so on, and you'll see it's always the case that these configurations form loops, okay? And so, and analogously, if you do the same, but now you focus on the X basis, you will see a soup of loops, okay? But in that basis, which is different, okay? So that's just to say motivate the whole thing. Let me see if I can organize this a little bit. Right. So analogously on the X basis, that's going to happen, but I'll let you think about it in terms of not satisfied plaquettes, but satisfied vertices, okay? and you'll see there's again a happy bunch of satisfied vertices and different loops, and I'll let you figure out what loops. Okay. Now the loops won't be on the dual lattice, but they will be on the direct lattice. Okay. All right. Now, so let me just write down the ground state. Okay. The ground state, say in the computational basis, in this basis. Okay. I'm going to tell you what it is. So, in this basis, the ground state of the toric code is a superposition of all the configurations such that all the plaquettes are satisfied. Okay, so configurations of this type. All right, so let's do it. Let's do it. It's a superposition over spin configurations sigma. So these are all the spins up and down. This is called collection, such that. Let me first do it this way. Sigma, such that for all sigmas, the products over plaquettes, let's say, the products over J in the plaquette of J are 1, okay? Which so it's an equal superposition. So there's basically we will require that this is a constant, and I'll tell you why in a minute. Or equivalently, because of this cartoon that I drew here, and the argument that I tried to explain and to observe is this is the same as an equal superposition of loop configurations on background of spins up, okay? So it's a superposition of all these configurations that look like this, okay? And clearly, as we said, this is an eigenstate of B, of all the B simultaneously, okay? Because every time you apply it, you will get a 1, and you'll get energy minus 1 because of the minus on each plaquette, all right? But then we have the, so then we can also ask the question, is this state also an eigenstate of AV? Because that was one of the conditions, right, like for the construction, because they all commute. And let me just give you a visual explanation for why this is true. It's basically, if this is a constant, if the wave function is constant for all the configurations where this is true, then when you apply this operator on that state, you'll get back a new configuration, okay, that satisfies the loops, okay? And let me show you how. And I already hinted that this is possible, right? So let's look at it, right? Let's look at it here, which is where I did it, right? So I said that before I flipped these spins, right? This was a configuration that was part of the ground state, right? And now if you think about the effect of this of a vertex. So what this spin operator does is flip spins in this computational basis, right? So if you apply a vertex operator to this configuration, what does it do? It goes and flips all the spins in the vertex, right? So then if we apply a V to this configuration, for instance, what do you get? You would get that you're flipping the spins in this plaquette, right? And so if you take this and you apply it to the ground state, what would you get? You get the same, right? Because when you apply it to, say, for instance, this configuration, you get the ones where you have the spins down. But then when you apply it, you're also applying it to the one where the spins are down, sorry, up, and so you will get this back. You see what I'm saying, more or less? And so basically, if you convince yourself, if you look at this more like slowly, you'll see that you will get, so if, or as long as the wave function is constant for all the configurations that look like this, then you'll get the same wave function back. Okay. Okay, good. So this is the ground state that's simultaneous eigenstates states of all the B and all the A in the Hamiltonian, and minimizes the energy, right? So what's the energy of the Hamiltonian, or the ground state of the Hamiltonian in this case is can you guess? If you apply H on this wave function, you'll get you get an eigenstate. So you get the energy, and the energy is going to be the sum over the plaquettes. So each plaquette gives you one. So it's the total number of plaquettes. Sorry, yeah, the total number of plaquettes minus the total number of vertices. Okay, so that's the ground state energy. Okay, all right. So finally, so I mean, like, so let me. Okay, there's a lot I could say about the ground state of the toric code, but I won't. Okay, so I just mentioned that that's the ground state, or a ground state. And I'm going to write down here what I like, the couple of things that I didn't say, or that I won't have time to say about it. But let me highlight what are the things that. So there's a lot more. A lot more about this Hamiltonian, for instance, ground state degeneracy. Which depends on the geometry of the system, or the topology of the lattice that you're using. There's a close relation to quantum error correction. And fractional statistics. So I mentioned fractional excitations. And more. So we talked about the ground state, but the excitations of this system are very interesting. They display this type of behavior where you get this emergent fermions and the emergent particles with fractional statistics. And so it's very interesting, but I guess for the purpose of what I wanted to explain next, this is going to be enough, okay? And let me go back to the slides for 1 minute. So recall that we constructed a model, a convolutional neural network that behaved in this way, right? Like, so if we had a spin configuration and we pass it through the convolutional neural network, it would output either two numbers or two vectors, right? It would output either, so the output is it's two numbers, right? Like for each configuration that you input, you get two numbers, this one and this one, all right? And so depending on your input configuration, so the function will output two different numbers, right? So one, we call it we call it the cold neuron and the warm neuron, okay? So you'll get, so the behavior that I tried to explain yesterday was this: if sigma was a ground state of this Hamiltonian here, of this part of the Hamiltonian, right? Then your cold, so the cold neuron, say cold and warm. So the cold neuron would be 1, and the warm neuron would be 0, okay? And if you input any other configuration, you get 0 here and 1 here, okay? That was the construction that I argued yesterday, that that was the behavior of this object here, okay, based on these filters, okay? Okay, now I want you to think about this object here, okay? We said that this wave function was a superposition of all these configurations that satisfy the constraint given by that piece of the Hamiltonian, right? The diagonal part of the Hamiltonian, or the B part of the Hamiltonian, okay? And so we said that for those configurations, this was a constant, okay? And for the rest of the configurations, you get 0, which is equivalent to this sum over loop configurations, okay? And so what I want you to identify is that this object, this wave function here, behaves the same way as the cold neuron of the model that we created yesterday, right? And so if we take this construction and we interpret it as the amplitude of the wave function, and we basically just get rid of the warm neuron, we just take the cold neuron, then that's this, right? Like we take this original neural network and we get rid of one of the neurons, then we get this. And then we can interpret this as this amplitude, okay? Okay, so that's good. And now what we do is we take that and we create a superposition or a quantum superposition of this configurations or these amplitudes, and then that becomes the ground state of the toric code. Okay. Yeah. No, the energy is not 0. The energy is what we said earlier, right? Like the energy is minus the number of plaquettes minus the number of vertices in the lattice. Okay? No, the for the whole system, yeah. Yeah. So suppose you went to the lab, okay, and you measured, you created this ground state, and you measure in the computational basis, right? You'll get configurations that look like this, right? That form these loops or that satisfy all those plaquettes. And the probability of observing those is constant and given by the output neuron, okay? Okay, so that was the story, right? And I guess what I wanted to say is, so this was me or us in 2016 thinking about, can we use neural networks to compute ground states, okay? So that's the background of the story. But it turns out that people have been thinking already about it since the 90s, right? So this paper, Artificial Neural Network Methods in Quantum Mechanics, where they solved very simple problems in 2 dimensions using neural networks, okay? And so that's part of history. Then there was this paper we published in 2017 or 2016, where we showed that the ground state can be, it's very simple Hamiltonian, but we showed that this ground state can be written down in terms of neural nets. And the most influential paper came around the same time, basically, or a little bit after our paper. So they did solving quantum many-body problems in general with artificial neural networks, okay, by Giuseppe Carleo and Matthias Streuer. They use a different architecture called restricted Boltzmann machines, and then they tackle problems, well, some problems that can be solved analytically, but also some problems for which there's no known solution, okay? So that's where I'm going right now. So can we solve more problems or problems that are a little bit harder for which there's no solution using artificial neural networks, okay? And to do that, I'm going to introduce an idea called variational Monte Carlo. So let me go ahead with that. Back to the Blackboard. So variational Monte Carlo. Okay, so given some Hamiltonian for which we can't find its ground state, can we try and guess the ground state, right? Or can we find a guess, right? Can we have an educated guess somehow? And this is all based on the variational principle that you may have seen. So let me state it. So variational principle. Okay, so suppose you have some sort of Hamiltonian, and imagine you know its spectrum, right? So psi n. So we don't know it, but we imagine we know it, right? So these are the eigenstates where n goes from 0 to the dimension of the Hilbert space -1. This dimension can be very large, so the dimensionality of the toric code was very large, was 2 to the number of spins in the lattice, so that's quite a lot. And so sometimes we can, when we don't know the solution, we can try and solve the problem numerically using exact diagonalization, but then because of the size of the Hilbert space, which can grow exponentially big, we can't, right? And so is there anything else we can do? Okay, so let's assume that the spectrum is not degenerate, and then you have the following, 2 and so on. And and then we propose a guess for the wave function, okay? So this is the wave function, and this wave function will have parameters theta. So this is a collection of parameters that we have in our wave function. So what we can do is we're going to assume that this set of eigenstates form an orthonormal basis, which means that they are orthogonal and prime, and then they, if you sum over this matrix, those matrices, you get the identity. Okay, so this is called completeness relation. So what we can do is we can then expand or write down this wave function in that basis. Okay, and for instance, basically you take this completeness relation and multiply the wave function. Okay, so this is exactly true. Basically what we do is we call this part the wave function in that computational basis, right? And okay, so now let's compute the expectation value of the energy on this wave function. So the expectation value of the Hamiltonian on this wave function, and let's see what we can say about it. All right, so we're going to call this E of theta. So it's not the ground state. So this is the ground state. This is E of theta. So this is equal to H. Okay. So what is it? So we plug this object here. Okay, the expansion in the eigenbasis. All right, and so what do we get? So I'll let you do it, but you get the following. Sum over n, you get n squared, and then you get n. Okay, so what you do is you plug this in here, and you know what you do is you know that these are orthogonal, and that you use the fact that these are the eigenstates of the Hamiltonian to get this, right? And so what we can observe is the following, right? That this is a sum over these terms, and the number, like among all the eigenstates, we order them, right? Like we have ordered the set of eigenstates. So if we take these ones here and we replace them by the ground state, then we get something that's larger or equal than this, right? So sum over n, so n squared, and then instead of en, I'm going to have the smallest of the eigenstates, right? And so this obviously is big, so this here is bigger than this because I've replaced all of them by a small number, or the smallest number among the eigenstates, and then so that doesn't depend on n anymore, and so we can bring it here. Okay, and this is what? This is the normalization of the wave function, which we've assumed that's normalized. So what we see is this, right? That expectation values of certain Hamiltonian over some wave function, this is always larger or equal than the true ground state of the system. Okay. So why is this important? Why is this as a good principle? Is because this gives us the opportunity or a tool to find upper bounds on the ground state energy. Okay, and so so okay, so that's good. So, but how can we use this, right? Like, so what we do usually is we have a tool here. We have a quantum state that has some parameters, okay? And what we do is we'll then go and try and find the wave function that's the closest to the true ground state by minimizing the energy E theta with respect to the parameters, right? So then, so that's what we will do. We'll find parameters theta such that we minimize E theta, okay? So this is basically find the parameter theta such that this function of theta is minimized, and that is the variational principle or the variational method. Okay, so how can we do this? So the hope is that if we have an ansatz or a wave function that's very expressive, that's very powerful, then then the hope. So let's say hope is that E of theta star, the one that minimizes the energy, is close to E0, which hopefully in some cases means that the ansatz is approximately equal to the true ground state, and then we can use that to study physical systems, okay? So that's the variational principle and the hope behind everything we do, okay? Notice that there's a similarity between machine learning and the things that I was telling you about in the few days. That we had so in machine learning we had this objective function J that depended on our parameters W, and that if we wanted the machine learning model to behave the way we wanted, what we had to do was to minimize this objective function or this cost function with respect to the parameters, right? And what we're doing here is very similar, except we changed this objective function and the fact that we had data for an objective function that's the expectation value of the energy, but that also has some parameters, right? And that we can also minimize such that we find a solution to a problem, okay? So this is one of those examples of that I was talking about. That was if you want physics-based machine learning, if you want, right? Like where you have a problem that's not given to you in terms of data, but in terms of a Hamiltonian or a physical principle and so on. And then we can use, say, similar techniques to approximate this problem. For instance, using gradient descent techniques, okay? So, okay, so of course, let's see a little bit of how, like what ingredients do we need to achieve this, to perform this, or to carry out this program of the variational calculation when we have very large dimensional spaces, right? Because as you can imagine, this computation of the energy may be tricky because this is a very large matrix. This wave function is also potentially very large. So if we wanted to do this exactly, this would be troublesome, okay? So I'm going to try and use the last 10 minutes to show you how we can try and estimate this object using a technique called variational Monte Carlo simulations. Okay, so let me try to explain that in the last 10 minutes. So we would like to estimate this object, right? E theta H. And let's say we're using a computational basis. We'll use a computational basis that is not this one. This one we don't know. If we knew, we had solved the problem. But we'll use some other one. For instance, the one we were using right before in the example. For instance, in the spin basis, right? Like in this computational basis. So this one is also orthogonal, and this is the the resolution of the identity. Okay, so what we do to come up with an estimator for the energy is we plug this and the energy twice. Okay, so let me do that. So E alpha theta is equal to, so I'm going to plug this identity here and here. Okay, and so let's say sigma and sigma prime, and you will have this psi theta, sigma H sigma prime and sigma prime. Okay, so let's see. So this I'm going to call this way. Let me do it. Sigma, sigma prime. I'm going to call this the wave function. And that computational basis, the expansion of that wave function in this computational basis, these are the elements of the Hamiltonian and written in this basis. And then you have the wave function again now for sigma prime. Okay, yes. Sorry, yes, here. So this is, sorry, yeah. Same as what we had here. Okay, so this is still horrible, right? Like, 'cause this is still a double sum over a Hilbert space that's potentially actually exponential, right? Like in the number of degrees of freedom in the system. So can we do something about it? And let me rewrite it in this way. So I'm gonna sigma and so theta, and let me have here the sum over sigma prime, H sigma sigma prime, and so okay, so far I have not done anything, but what I'm going to do is I'm going to multiply and divide by the complex conjugate of this object. Okay, so sigma, and then divide here, assuming this is doable, right? Like this is different from 0. Okay, so this becomes the amplitude square of the wave function, right? And this I'm going to call the local energy that depends on sigma. Okay. Good. So now we have a rewriting of the expression that looks a little bit better in some sense. In that there's exactly, so this looks like the expected value, the statistical expected value of what object? Of E log, of the random variable E log of sigma. Okay. Okay. Is this okay, right? Like, and expected value with respect to this object here, which because of the wave function is normalized, and this number is always positive, so we can think of as a probability distribution over sigma. Why? Because this is a positive number, and the normalization of the state tells me that theta, that this is 1. Okay, so it is a probability distribution. Okay, and so okay, so this is the first, the second ingredient. So can we use the fact that this looks like a probability distribution to do something, to compute it, right? So I'm going to tell you, or remind you of statistics a little bit. So something called the law of large numbers. Okay, so let me write it quickly here or here. So law of large numbers. Of large numbers. So the law of large numbers is the following. So suppose you have a die, okay, and you roll it 100 times or many, many times, okay? So roll dice ns times, where ns is a large number, okay, large number of times. So then you get outcomes. Sometimes you'll get a 1, sometimes a 2, a 6, a 3, a 4, a 5, a 1, a 2, and so on. And the law of large numbers tell you that, okay, you get outcomes xi, where I is 1 through ns, right? So these are the outcomes. This is 1, 2, 3, etc., right? So the law of large number tells you that the limit, or let me first call this, so x, so we'll call the average, so we'll call this, right, like the ns, sum over I from 1 to ns of xi. So this is the empirical average of the over the outcomes that you got on your L or your NS trials, okay? So the law of large numbers tells you that the limit of NS going to infinity of NS is the expected value over the probability distribution of flipping dice fairly. Okay, so I from 1 to 6 of Pj, Xj, which is, so P is 1/6, because this is a fair die, okay? And you have the average over the different outcomes, which is 1, plus 2, plus 3, plus 4, plus 5, plus 6. That's 3.5, okay? All right, so this is part of it. So the average over the outcomes converges to this, which is the expected value of x, or x, yeah, okay? But also that the variance of your averages becomes smaller and smaller as we make n is larger and larger, okay, in a specific way. So, and the variance of x and s is basically where this is the variance of each individual trial, okay? So this is roughly, of course there were some assumptions here, let me write it down. So each xi is independent. And that the variance of x, or of the each of the x, or if each of the trials is finite and equals to sigma, okay? So this is the important thing, that if you draw random numbers according to this distribution, such as like flipping a coin or a dice, then you average these numbers, so this average will converge to the expected value, and with a variance that decays, the fluctuations decay quickly with the number of times you repeat the experiment, okay? And as an exercise, I'll like ask you to show this. exercise. Okay, under these assumptions. Okay, so this is great. Now, how can we use this for variational Monte Carlo? So what I've shown here is that the energy can be written down as an expectation value over the local energy on this probability distribution. So if we wanted to compute this energy given some sort of wave function, then what we need is the possibility to compute or to sample the wave function according to this probability, according to, well, the wave function squared. That's the first thing. And we can do a bunch of them, right? Like NS is large. And then if we do that, then we can average over this local energies, okay? Yeah.
Sorry, I don't know if I'm anything, but what is the goal localized energy, and how can you be sure that the psi function divided is universal?
Yeah, so that's a trick that we've done. It only works if the wave function is different from 0. But when you do the sampling, if this wave function is 0, then the probability of observing that configuration is 0, and you will never see it, and you will never have trouble computing the local energy on the configurations that you see in the sampling, and the estimator is unbiased. So it's a good question, and you shouldn't be dividing by 0, right? But in practice, you will never have any problem with the estimator of the energy, because you will never see such configurations. Okay. Okay. So you call it local energy because it depends only on this local configuration. Okay, that's roughly the idea. There's one more. I'm missing one thing, and it is, so we replaced one sum, one exponential sum, okay, by a finite sum with ns terms, right? So we're getting rid of an exponential sum, and we're replacing it with a few terms or 1,000 terms. I don't know how many samples you need, but the local energy contains, again, a second sum, okay? And the sum is also in principle exponential, okay? And so we'll have to restrict the type of Hamiltonians that we can handle with this technique. And let me write this down because it's important. So we'll restrict this to Hamiltonians which are local. So E log of sigma is equal to sum over sigma prime of H sigma prime So local Hamiltonians. So we'll restrict to Hamiltonians for which, given a configuration sigma, there's only a polynomial number of rows in the Hamiltonian for which this Hamiltonian is non-zero, okay? And so, okay, so only, so given sigma, only of for which is different from 0. Okay, and now we're in business because now we've replaced, or now we have one sum that is exponential that we've converted into a sum over a few terms with some uncertainty, but averaging over a quantity that is only a polynomial number in the, say, in the number of spins of the system. And And with that, we can compute the energy, okay? Right, and then so that's how variational Monte Carlo works. What do we need? We need wave functions for which we can sample, local Hamiltonians for which we can compute the local energy quickly, and that gives us a strategy to compute the energy. I'm gonna skip the last part I had, which was how do we optimize the energy, because we needed to optimize the energy. I'll explain that tomorrow in 1 minute, okay? Now we can take questions. So we need a wave function that's a guess that we have. So we come up with that guess. And then you do the optimization of the energy, and then you test how good it is, right? And where we're going is as you can guess, we mentioned that we're going to represent this wave function in terms of what? In terms of a neural network. And the example I gave was only to motivate or to argue that this is a good idea. And we gave the example of writing down the ground state of the torque code in terms of these neural nets. And that's what we'll do, but now for Hamiltonians for which we don't have a solution. Okay? Yep. Yes, because so what we had here at the beginning was we had a double sum, okay? And these two sums run over exponentially many configurations because the size of the Hilbert space, say for spin 1/2 systems, is 2 to the n, and we want to deal with systems that are large. So where this number is astronomically big, right? Like the size of the number of atoms in the universe and so on. And so we had to do something about those two sums, right? So one, through the law of large numbers, we converted into a sampling problem. And so instead of 2 to the n, we'll collect ns samples, okay? And be happy with the fluctuations we get, or the deviation from the mean due to the variance that we get. But let's say we collect a few thousand samples, and so that we can do in our computers. But we had a second sum here, the sigma prime, that we had here. We call it the local energy. Okay, is this, and the sum, I didn't do anything about it. I didn't mention it, right? But the sum will have to be computed, right? Because for each configuration we see when we sample, we had to compute this average, so we need to compute the local energy for every single one of the samples that we see in the sampling procedure. And then so we have to be able to compute E-log 1,000 times, or a few thousand, ns times, right? The number of samples times. And so I have to be able to do it. But in principle, for a generic Hamiltonian, the sum is exponential. It has 2 to the n terms, okay? And so what I did was impose a restriction on h, okay? Such that we call it local Hamiltonians, and they're such that given one spin configuration sigma, among the ones that we sampled, for instance, there's only a small number of terms. I said polynomial, so polynomial is typically in computer science, you say this is computable or is easy to compute in the number of, say, spins. So a polynomial number of spin configurations, sigma prime, for which h sigma prime is different from 0. Okay, if for the rest is 0, then it means that the sum becomes only a polynomial number of terms. And so that means we can compute it quickly. It's going to be an assumption, right? Like we have to assume that the Hamiltonians that we'll be dealing with satisfy this, which luckily is most Hamiltonians we see in nature. Most Hamiltonians in nature are only a few usually a polynomial number. So it's a good assumption. So it is an assumption. So you cannot do variational Monte Carlo on complicated general Hamiltonians. It's not possible. Yeah, it is a good enough assumption, yes. Because most important Hamiltonians are pretty local. Yep. There's many things you can do, right? Like you bring all the knowledge you have about the system and come up with a good wave function based on your understanding, and then you go with it. But there's other philosophy, which is the one I was discussing yesterday, is you can use neural networks. And these are universal function approximators. I guess at some point I mentioned that a neural network of this type, okay, with fully connected layers and only one output neuron. So if you let the number of nodes or hidden states in this neural network grow arbitrarily large, you can represent any function. Okay, so then it means you can represent any ground state. Can you repeat the question? I mean, in principle, if you take this architecture and you use it, in principle, you could represent, and in that sense, the whole thing is unbiased. But of course, when you go and try it, and you make it bigger and bigger and bigger, then this optimization problem becomes very difficult, okay? So then you have to go back a little bit and say, okay, can I add some sort of knowledge about the system? So it looks very promising and is a very powerful idea, but in practice, you have to do a lot more. But in principle, this is a way to avoid having to guess a good wave function. It's a matter of a principle, but in practice, you go and try, and this doesn't quite work. It's very hard to optimize. So you go back a little bit and bake some information about the wave, about the system you have, and then you improve things by adding the knowledge you have. I mean, you can use CNN, you can use fully connected architecture, you can do many things, and yes. Yeah. All right. So, yeah, so you take the wave function, whatever it is, and you square it. And that becomes your probability. In which case? Yeah, so for the toric code, for instance, so we're not interested in that because that can be solved exactly, but if you took the architecture that I gave you and you took the exact same filters and so on, and you interpret that as a wave function, and you run this whole program, then this is what? What would you get? Minus the number of plaquettes minus the number of vertices, exactly. You'll get that number exactly. But for that case, we just don't need, we know, right? Like, but you could do it. But we'll deal with Hamiltonians for which there's no solution, so we'll see something else. Yep. Yeah, so they're both equivalent in principle, right? Like if we could compute this energy analytically, but we can't in general, but if we could, then we would do the minimization analytically. We could, but usually we have a bunch of parameters, right, in the wave function, and so solving this problem analytically is very difficult, and so we have to use these techniques. But in principle, it's the same thing. It's for large systems and for complicated wave functions that you need this. Yeah, that's a good, excellent question. Yeah. No, so there's no data. I didn't mention any data at all, right? I just had a Hamiltonian with some assumptions, and that's enough, right? Like that's what I meant by physically driven learning, right? There's no data. So in the first class, I said there's two types of learning. One is learning based on data sets, and then there's learning based on, say, physical laws or physical problems. So this is what specifies the problem, and that's the only thing we use to solve it, right? Of course, you could combine data with this, but so far in this scheme, there's no data. Mm-hmm. Yeah. So let me give you one problem, okay, for you to play with. One exercise before you go. And it's related to your question. So, sorry, I'm taking too long, but so the 1D harmonic oscillator. So Hamiltonian is minus 1/2 d2 dx2, say plus x squared, okay? Now, using the variational principle, so use this wave functions, right? Like beta x equal to c 1. So estimate the energy, okay? And find the optimal B star that minimizes the energy, okay? No, so you have to so this C is a normalization constant. And beta is the variational parameter. Okay? And so that's the first point. And then the second one, take this. Again, E of beta and B star. So which one do you think will give you the best energy? A or B? Yeah, B, and why is that? And why? And but this one is also has the same shape, right? Yeah, because this one contains the solution. So this one will give you the exact answer, whereas this one not. And so according to the variational principle, E of beta is always greater or equal than the exact solution, okay? So just play with this, okay? And try and solve the problem. Okay, good. So for this, you don't need Monte Carlo, of course, because this is very simple wave functions, but it helps you to think about the variational principle. Thank you.